Hi guys, welcome to part 4. In this we are going to see problems from one-dimensional wave equation with a non-zero initial velocity. See, the problem given is a tightly stretched string at endpoints x is equal to 0 and x is equal to L is fixed. Okay, and initially at rest in its equilibrium position. If it is set vibrating, giving each velocity lambda into Lx minus x squared, then show that the displacement of the given string is y of x comma t equal to 8 lambda L cube divided by a into pi power 4 summation n equal to 1 to infinity 1 by 2n minus 1 the whole power 4 into sine 2n minus 1 into pi x by L into sine 2n minus 1 pi at by L. See, the first thing we have to see from the problem is the boundary conditions. The boundary conditions is the two ends are fixed. That is, at x is equal to 0, it is fixed. The meaning is the displacement is 0 at x is equal to 0. Similarly, at x is equal to L also the displacement is 0. And it is in equilibrium position, it is given, and it is set vibrating at each of its point velocity. So velocity is given. Velocity means the initial velocity, that is dou y by dou t of x comma 0 is given. So always for doing problems under this case, the non-zero condition should be the last one, that is it should be the fourth condition. So the fourth condition is given. And it is at rest it is given. So we can consider the initial displacement, that is y of x comma 0 as 0. Then finally we have to show the displacement equal to this one, to the given thing, and we have to prove this as the displacement for the given conditions. Okay. See, now we know that the one-dimensional wave equation is dou squared y by dou t squared equal to a squared into dou squared y by dou x squared, and we know that a squared is nothing but tension by mass. And here the correct solution is y of x comma t equal to a cos px plus b sin px into c cos pat plus d sin pat. Let us take this as our equation number 1. Now, the boundary conditions are y of 0 comma t equal to 0 and y of L comma t equal to 0. That is what it is, the two ends are tightly stretched at x is equal to 0 and x is equal to L mean. Okay, so that's the meaning of this. So at 0, at x is equal to 0, no displacement. At x is equal to L, no displacement. And also it is released from rest in its position, it is given at see, if it is set vibrating, okay, initially at rest is given, so that means the displacement is also 0. The velocity is given here. So now let us apply the conditions one by one. So these two are the initial conditions and these two are the boundary conditions. So now let us apply y of x comma t, that is the condition given. In that let us substitute the first boundary condition, y of 0 comma t equal to 0. So when y of 0 comma t means that is nothing but equal to 0. So in the left hand side we have to substitute 0. Substitute x as 0, a cos 0 plus b sin 0 into c cos pat plus d sin pat. See, in this, when x is taking the value as 0, sin 0 is 0 and cos 0 value is 1, and therefore we will get this as 0 equal to a into c cos pat plus d sin pat. So from this we know that the first two boundary conditions are valid for the values of t greater than 0, and therefore these two summation cannot be equal to 0. This is treated as a single term and its value is not equal to 0, and only option is a equal to 0. Now we are going to substitute a equal to 0 in the equation 1. Therefore we will get y of x comma t as b sin px into c cos pat plus d sin pat. Now in this we are going to apply the second condition, second boundary condition, that is y of L comma t equal to 0. That is when x is L, then that y of L comma t is replaced by 0. Okay, that is the displacement at x is equal to L is 0. So y of L comma t is b sin pl into c cos pat plus d sin pat. See, in this, in the from the previous equation we have concluded this particular term is not equal to 0, and by the condition we have the left hand side equal to 0, b into sin pl into c cos pat plus plus d sine pat, and we know this is not equal to 0. Therefore, we are left with the two options b and sine pl equal to 0. If b is 0, then the equation y of x comma t will become 0. That is, the displacement will be 0. So, which is not possible. Therefore, the only option is sine pl equal to 0. If sine pl equal to 0, then pl is a multiple of n pi, and therefore we get p equal to n pi by l. Okay. So, in this, if we substitute p equal to n pi by l in the above equation 2, we get y of x comma t as b into sine n pi x by l into c cos n pi at by l plus d sine n pi at by l. Okay. See, now we have to apply the third boundary condition, which is y of x comma 0 equal to 0. So that is y of x comma equal to 0 means we have t as 0 in this case. So if I substitute t equal to 0 in this one, it is c cos 0 plus d sine 0. Okay, sine 0 is 0. So 0 into anything is 0. So we will be having 0 equal to b into sine n pi x by l into c. Now bc is a constant. Okay, that into sine n pi x by l will be there. So b is not equal to 0. Already we have proved sine n pi x by l is not equal to 0. Therefore, the only option is c equal to 0. So let us substitute c equal to 0 in the previous equation. So when you then we have y of that is in the equation 3. So we get y of x comma t as b sine n pi x by l into d sine n pi at by l. Okay. So in this, b and d are the two constants. Let us take that as a single constant, say some b1 or whatever it is, into sine n pi x by l into sine n pi at by l. See, we know that by the superposition principle, the linear combination of this can be a solution to the problem, and hence we conclude the most general solution as y of x comma t equal to summation n equal to 1 to infinity bn into sine n pi x by l into sine n pi at by l. Okay. See, in this, we have to apply the last condition, that is the non-zero velocity. So that is our last condition. So for that, we have to differentiate the most general solution equation, which is nothing but our equation number 4. So if we differentiate this with respect to t, x is treated as a constant because we are doing the partial differentiation. So dou y by dou t of x comma t equal to summation n equal to 1 to infinity bn into sine n pi x by l. Now differentiation of sine n pi at by l is cos n pi at by l into n pi a by l. Okay. See, in this, we have to apply the fourth condition. Our fourth condition is dou y by dou t of x comma 0, which is nothing but equal to lambda into Lx minus x squared. That is the non-zero initial velocity. Now in this, if we substitute t as 0, our cos 0 will become 1, and therefore we will be having bn into sine n pi x by l into n pi a by l. See, in this, we know that this is a constant. N is a constant, pi is a constant, a is a constant, as well as l is a constant. So, in this, we are multiplying bn and n pi a by l, and we are treating that as one more constant, say capital Bn. So, summation n equal to 1 to infinity bn into sine n pi x by l will be here. See, now what we need is the small bn. So after finding this capital Bn, we have to find what is our small bn. This is nothing but a half range sine series in the interval 0, l, and we know f of x is nothing but the initial velocity, and it is given by lambda into Lx minus x squared in the interval 0 to l. So now we have to find the capital Bn. Remember, the capital Bn is small bn into n pi a by l. So after finding this, we need to find what is our small bn for substituting it in the most general solution. So now, as usual, we have to apply the Bernoulli's formula. We know that f of x is the non-zero initial velocity. So substitute it into sine n pi x by l into dx. Take this as u and this as dx or dv. So apply the Bernoulli's formula here. 2 lambda by L is a constant, so we have taken it outside. So u into v1 is nothing but the integration of sine n pi x by L, so which is minus cos n pi x by L divided by n pi by L, and differentiate this, so that is our u dash. So my L minus 2x will be there, then again we have to integrate, so we'll get minus sine n pi x by L divided by n squared pi squared by L squared, and again differentiation of this is minus 2 with respect to x we are doing, and integration of this is cos n pi x by L, and we have one more n pi by L, so altogether we will get n cube pi cube by L cube. Now the limit is 0 to L. See, if we apply the upper limit x is equal to L, L into L, you will get it as L squared minus L squared will be there, so it is 0. And for the lower limit also, if you substitute x is equal to 0, this will be 0. So the first term will not exist for the upper as well as for the lower limit. Now coming to the second term, we have x as L. So if I substitute x is equal to L, so it is L minus 2L, but even then you have a sine n pi L by L. So L will get cancelled, you will get n pi. So sine n pi value is 0. Similarly, if we substitute x as 0 here, even though we have L here, sine 0 value is 0. So the first two terms will not be there for the upper as well as for the lower limit. So we will be left with only the third term, and the third term is having the denominator n cube pi cube by L cube. We are taking it to the numerator, so it is 2 lambda by L, and this will go to the numerator. It is minus 2 L cube divided by n cube pi cube into cos n pi x by L over the interval 0 to L. The limit is 0 to L. Now let us apply the limits one by one. Let us take the constants which are independent of n outside, and therefore we will get this as if you want here when you apply L here, it is a cos n pi value is minus 1 whole power n, and if you apply x is equal to 0, you will get cos 0 value is 1. Okay, so now we get that capital Bn equal to minus 4 lambda into L square divided by n cube pi cube into minus 1 whole power n minus 1. Here capital Bn is nothing but small bn into n pi a by L. Therefore we can find Bn from this, and here this L will go to the numerator, it is L cube now, and this n will come to the denominator, it is n power 4. Already you have a pi cube, so it will be pi power 4 now, and you have a. Now this is minus 1 whole power n, you know this is the value of cos n pi, and this is the value of cos 0. So upper limit minus lower limit is there, and you know whenever these type of conditions are coming, we have to discuss the odd and the even nature of n. So when n is even, I will, for example, let me take with the smallest value, say 2. So minus 1 the whole squared, it is plus 1. Plus 1 minus 1 will give you 0. And for any even values, it is going to be 0. So we conclude that Bn value is 0 if n is even. For example, if n is odd, let me take with the least value, say 1. So minus 1 to the power 1, it is minus 1. Minus 1 minus 1, it will give us minus 2. Minus 2 into minus 4, it will be 8. So always you will get 8 for any odd values. So it is 8 lambda L cube divided by n power 4 into pi power 4 by a. The meaning is, if n is taking the value as 1, the numerator is always 8, whereas the denominator will be 1 power 4. If it is 3, the numerator is 8 lambda L cube, whereas the denominator will be 3 power 4. Like that we will get the values. Therefore let us substitute the values in the general equation. Therefore we get y of x comma t as summation n equal to 135 and so on to infinity. The Bn value is what we have here. It is 8 lambda L cube into divided by n power 4 pi power 4 a into sine n pi x by L into sine n pi at by L. See here, the summation is valid for 135 and so on to infinity. Suppose if we want to write it as n equal to 1 to infinity, we have to replace all the n by 2n minus 1. So this is the displacement required. So y of x comma t equal to 8 lambda L cube divided by pi power 4 into a summation n equal to 1 to infinity. I have replaced the n by 2n minus 1. So it is 2n minus 1 the whole power 4 into sine of 2n minus 1 into pi x by L into sine 2n minus 1 into pi at by L.